This lecture introduces different types of system of linear equations. So the first types of system of linear equation is the inconsistent system. So a system is inconsistent when it has no solution or when the solution set is empty, no solution at all. And in cases where the number of equations is more than the number of variables, which means the number of rows is more than the number of columns, then your system is called overdetermined system. And if you have an overdetermined system, most of the times the system is inconsistent, mostly inconsistent, if a system is overdetermined. Okay. Well, and then if your system is consistent, that means the system has at least one solution. So if you have a system and you could find at least one solution for that system, then the system is consistent. And in the cases when the number of equations that is less than the number of variables. So when m is less than n, where m is the number of equations and n is the number of variables, then the system is called underdetermined system. And if a system is underdetermined, most likely that system is consistent with many, many solutions. All right, again, most of the time when you have more variables than equations, then your system is more likely to be consistent with many solutions. And then we have homogeneous systems. A homogeneous system is a system that is always consistent. And homogeneous systems is a system when the constants on the right side of the equation are all zero. So if you have a system, right, and then you convert it to an augmented matrix, and if all the entries on the most right column of the augmented matrix is a zero column, that means this system here is a homogeneous system. And homogeneous systems are always consistent because you have a trivial solution for this homogeneous system. A trivial solution is a solution when all the variables are equals to zero. So x1 equals to x2 equals to x3 equals to 0 is at least one solution for this system. Okay, again, a homogeneous system is a system that has at least one solution, is always consistent, at least one solution, and its homogeneous system has the constant column or the constant matrix here is a zero column. Okay, this is the augmented matrix of a system, of a homogeneous system, and you can see that I don't care about the coefficient matrix. If the constant column is a zero column, then the system is homogeneous, and you know that the system is always consistent with one trivial solutions of zero. Okay. Now there's a theorem in the book say that if a m by n homogeneous system of linear equations has a non-trivial solution if n is greater than m. What does that mean? That means this is a homogeneous system. So I just want to sketch out a system, right? homogeneous system, and m by n. So m is the number of equations and n is the number of variable. So if x1, x2, 2, xn. So you have n variables, right? And then you have equations, m equations. So if you're using indices for all the entries, you will have, so this is the first equation here. So this is the first equations, second equations, and go to the m equations. Again, m equation and n variables. That's what we have here. All right. So now, is this a homogeneous system? And you want to show that this system has a non-trivial solutions. That means this system here has a solution that is not just zeros. So we know that a homogeneous system has at least one trivial solutions. But then what we want to show is we want to show that this system here has a non-trivial solution. How can we show that? So if we start with a, so let A, right? Be an m by n homogeneous system. Okay. So this is the condition m and a homogeneous system. Then, and we reduce A to reduce row echelon form. So you start with A. So this matrix A here, right? Start with x11, right? x12, x1n, and x21 down to xm1. And you go to xmn. And then your constant columns will be just 0. Okay. And when you reduce it to the reduced row echelon form, and then 0 will be just, it doesn't matter what operation you apply to 0, it's just 0. And then you have, since you have n columns, that means you will have at least n pivot positions. You have n, well, you have m row, so that means you have at least m pivot positions, right? So pivot position number 1, number 2, and to number m, because you have m rows. You have m pivot positions, and each of the pivot position will correspond to one pivot column. So the pivot column. Okay. This is another pivot column. Since m is less than n, that means the number of pivot columns will be less than the number of variable. Since thus there is at least one free variable, because each pivot column corresponds to each leading variable. So you have less number of leading variables compared to the total number of variables. That means you have at least one free variable. If you have at least one free variable, that means the system will have many solutions. And if the system has many solutions, that proves that the system here has a non-trivial solutions. This is what we want to show. Okay. And then there's another theorem about the system of linear equations. And if a system of linear equation is consistent, right? If and only if the rightmost column of an augmented matrix is not a pivot column. And then if you encounter a row of the form here in your augmented matrix, then your system is inconsistent. So we can refer to this example here, right? And this system we show that is consistent is because when we try to reduce this augmented matrix to the reduced row echelon form, and we encounter a row in this form. So a row in this form is a form when the rightmost pivot position is in the column, is in the constant column. If that was happened, then the system is inconsistent right away. We don't have to finish it. We know that the system is inconsistent. And that is what a theorem is, right? And reversely, if a system is always consistent, if the rightmost column of an augmented matrix is not a pivot column, that means the rightmost column should never be a pivot column, then the system will be consistent. So an example for that to illustrate that theorem is here. So first, if you have your equations, right? And then when you reduce, and then you have a constant column 2. And then when you reduce this matrix here to the reduced row echelon form, this system will be consistent. The system will have at least one solutions if the rightmost pivot columns here, pivot positions. This is the rightmost. The rightmost pivot positions is not a pivot. The rightmost pivot positions is not in the rightmost column of an augmented matrix. Then the system A is consistent. Which means A has at least one solutions. But in another case, right, if the reduced row echelon form of A is in this form right here, when the rightmost pivot positions is in the constant column, if this is what happens, this is the rightmost pivot positions, then you encounter, and then you have 0, 0, 0 here, right, as the form of the last row, and you see that this is the rightmost pivot positions here, and this system A is inconsistent.